Hello guys. All right. So we decided to distribute our processing logic. We decided to distribute our services. Fine. Great. Now we have to deal with data. Data integrity across services. You know, the promise of a microservices architecture, or the deal there, is that each service has to own its data. Fine. Then, what about when, as you can see here in the diagram, the order service needs to notify another service of certain data updates? That is where asynchronous messaging comes into play. So typically, what do? First, we initiate a database update for the order service. Then we notify interested services that, for instance, a order created event has arrived. That topic, that channel usually receive the payload, let's say in JSON. The order service continue serving its own functionality. Now the payment service, which is the one interested in this kind of messages, consumes that message, does the necessary payment, external payment communication, and updates its own database. Okay, we rely on something we call eventual consistency in this kind of event-driven architecture. Consistency. So we say that it is fine that data is not consistent in real time, but we know that eventually data will be consistent across both the order service and the payment service. Now, what can go wrong usually in this kind of setup, guys? All right, so we decided to call in our order processing, for instance, we decided to call the order repository dot probably update operation. Fine. That's the first line of code. The second line of code now has to notification, probably service, dot notify or send or whatever method we have there. Now, usually we do that, but we forget that this second operation here can fail. What happened in this situation? The ordering service update its database, continue processing its own logic, unaware that this event notification or this message didn't arrive into the message broker, leading to inconsistency of data across services. In this case, the payment service unaware that a new order was created. Thus, no payment is attempted. Another use case, for instance, in case you are not working with a synchronous processing on your order service here, the update may fail and the notification gets sent to the payment service. Another bigger issue. We don't have an order data here updated, but we have a payment being generated. That's risky, guys. Let me show you a different view of that same flow here. I used mermaid.live to generate that sequence diagram, by the way. So you can give ChatGPT or whatever Gen AI you are using, you give it the diagram, and it can generate for you the code you can copy and paste in mermaid.live. And that's what you can get. So you see the order service, again, updating the database as a first step and sending the event notification to the message broker. The payment service reading that event, calling that payment gateway, and persisting the payment result in its own database. The problem is that the write and publish are not atomic. It can't happen as a single unit of processing. One failure, either on this side, on the database update or the event notification, and everything goes wrong. Now, let's see the pattern that help us solve this kind of situation. It's called outbox pattern. The name outbox you create in your own database. It can be a relational database. We're talking about the order data here. You create a table specific called the outbox table. You do your own processing to update the database first. Then you go and update that outbox table in the same transaction in an atomic fashion, where you wait for the transaction to commit trx.commit. Once this operation succeeds, this means the database gets updated and that outbox table gets updated. The new thing introduced here is a processing service, an event processing service, responsible of continuously polling that outbox table, all right, for changes. And once it detects any change with a certain mechanism where you can have a field in that table mentioning the time plus mentioning the sequence ID as well. I don't want to enter into the detail of implementing that specific outbox pattern, because in another video we're going to talk how this is implemented out of the box for us in several cloud providers components. Once it detects that really there is a database update that didn't fail, all right, an event is sent to that broker that can be as well an order created topic. Now, and only now, you can be sure that the payment service, once it receives that order created message, that you will be sure that there is no database update failure back from the originating service. That is the idea behind transactional outbox pattern, as simple as it is. Implementing it yourself, writing it yourself, isn't that simple. Doable, but isn't that simple. Because the polling mechanism you have to do may have its own tricky logic there. Similarly, uploading that diagram to Mermaid, we can have that same sequence diagram updated. The order service updates the business data, as you can see. Insert the event within the same transaction in that dedicated outbox table. Then the processing service, using a polling mechanism or a change data capture, we're going to see in a future video we're going to talk about. Read that record and does the publishing necessary, and the flow proceed from the payment service, calling the payment gateway and updating its own database. So you see now we have the outbox table taken as a source of truth for the event processing service here. That is how we make sure both updating the order, the originating service, and sending the event is happening in some kind of atomic fashion. Now, this doesn't mean that we do not have trade-offs, guys, to consider. Very important things to be aware of. First, don't ever send events if the transaction rolls back. Be careful about this issue. You don't want to send, or you do not want your event processing service to read that a new record was created in the outbox table even when the transaction fails. That is why probably it is better to use something that is there already for us and not writing it yourself. Unless you are in a situation that you can't use a cloud component, that is where you write it yourself, but be careful about the implementation detail, because there could be some situation where database isn't well updated and the outbox table gets a record that isn't committed yet, and that processing service can read that record and send the event, leading to the same handicap situation that we started with in the beginning. That's the first thing to consider. Once the transaction in both tables, the ordering table and related entities updated, and the outbox table have a record that is ready to be consumed by the processing service. Now, even when you try to perfect that logic, you have to expect that duplicate messages can arrive. For instance, the order created topic can have two similar messages arriving, two similar messages arriving at that same topic, and that is an issue we have to always consider happening due to bugs, due to the originating service having an issue on a processing, a runtime issue causing it to restart and leading to resending that same messages. That is something we have to always take into account when dealing with distributed systems, guys. When you have two similar messages, if you do not factor that into account in your consuming service, which is a payment service in our case, if you do not make it what we call idempotent, I always find it difficult to pronounce this word. What does idempotent mean? It means that if you receive several requests with the same information, you have to treat it as a single one. That is where you can do checks for existing, probably correlation ID or existing order ID that is not being processed yet before sending it to the payment gateway. If your processing service or consuming service is responsible of inserting a record, you can do some kind of as well upsert implementation there. Check if record ID is already there. That is your responsibility as consuming service. In order not to process that order twice, in order not to submit or charge that customers twice. That is a very common issue we usually see. Now, I left that first consideration here to the end because preserving the order of events in which it arrives is important only if you are considering the event sourcing pattern, where in this kind of system, auditability is your main architecture characteristic you want to support. In this kind of event sourcing architecture or patterns, you want to preserve the order of events because you want to reconstructure those events in order to get to a certain state. So the order of events arriving at the payment service is very important in this event-driven architecture. I may do a different video specific to event sourcing and its own need, where there are policies or you are working in an industry that forces you, that has policies to force you, that you want to always go back in time to know what is the state of a certain customer information where. For instance, we want to know back in previously, like 2 months ago, what was the balance of that specific account. That is the kind of stuff that you can get with event sourcing architecture. It's very complicated. You can use it only when need be. And the transactional outbox pattern comes into play when dealing with that kind of architecture. So that's it, guys. See you next time.